Oh, right. Whoa, what's this? And then do. Ooh, okay. Great. So let's kick off. So this then lecture 5, I think, and we're going to change a little bit tack and start talking about the last bit of this course, right? So what I've really seen, having sadly I had to miss a few lectures by Neil, but I've watched them on the video. But we've seen this like painting a broad picture of what it means to work with data and to look at what this pipeline and a lot of what it's been, right, has been raising a lot of questions. So we're going to try and continue in that theme a little bit. So if we take these 3 words then, right? So we have the accept part, how to get and combine data sources for a potential problem, right? And then we've had this assess, which is things to do with data before you have a question. And a lot of this have been actually reflecting about the types of problems that appear and the decisions that we already do here and how they're going to affect us further down the line, right? And now we are going to start talking about this address part, which is really the easiest part of all these things, right? So the address is like, what can you do when you already have the data and the specific question to answer, right? This is a much, much simpler scenario. So I had a look and tried to like do this thing about how do we actually reflect about specific, how do we reflect about specific problems or just thinking about how we gather data, these questions, without actually knowing what we're doing specifically. There's tons of courses which might be, well, we're looking at this specific task, but then we've gathered all of this already, right? Then maybe there is some assess part which is giving us tools, and these are really stuff that are feeding into the rest of it. And here on this end, there's tons of courses, right? There's tons of different modules on this. And there's also, if you continue on and looking at the 4th year, we have even more. It's basically tons of them here. I couldn't fit them all, right? So that reflects kind of why this is, or when you think about why is that actually? Well, we're a university, right? And universities are really good at teaching things that are kind of done. Like we made a science of this and we know exactly how to do this. Great, here's how you do this, right? Now, I think part of this course has been, as Neil started off saying, I don't think data science is taught well anywhere, right? Possibly not here either, right? We're in this space where we're trying to figure out lots of stuff, which means it's really, really hard to give you a very super clear curriculum of what this is. It's actually really hard to make a course out of it, because a little bit disappointing is that you'll probably leave this course more confused than you were when you started off doing it, right? But now I think that's the really exciting thing, because you will know the questions that you need to address. And that's possibly quite a bit more valuable than us trying to do this, a very, very clear narrative around this thing, and then say, this is how you do it, because it's going to be wrong. most likely, right? Okay. So another thing that I thought, then a little bit of an ethos of a lot of things that I heard during this part, the first bit of the course, is that we think about the address part, which is very much going to be machine learning methodologies. We need to put that in context of data and also importantly, the humans who use this, right, towards the end. So rather than just giving you now, here's a couple of algorithms, they do this end, right? We're going to try and contextualize machine learning a little bit more. And again, this gives you lots more problems to think about. So I wanted to start with this curve to motivate what this lecture, the first one, is going to be about. So can someone tell me what they think this curve is? Or what it symbolizes? So, okay, I'm going to start off by, this is a curve that I overheard, or is something that Neil said. I'm not sure if he said this in this course, but what I'm trying to symbolize with this curve is that the black curve is machine learning exploding exponentially in terms of interest. And then this bell curve here has clearly two parts, one which goes up and a red one which goes down, right? And I think I agree with this, with Neil, is that there was a huge part of our careers where we spent going around convincing people to do machine learning for lots of stuff, right? That was like, you have to do this. You're so stupid about what you're doing. You need to use this new tool to start doing stuff and it will all be much better. And then there's a point, and I think Neil doesn't really, none of us really knows where this point is, when we started realizing, whoa, things are going really wrong when you're applying this. And then the phase of trying to stop people doing machine learning started, which is kind of what a lot of this course is about, right? Of actually trying to hinder you to actually do machine learning and really think the problems through before you get to this stage, right? Because a lot of, I think, the societal issues that we have is that people have these technical solutions for everything, and they start doing that first, and things go really, really wrong, right? What this curve also shows is that we're like machine learning hipsters, right? Because when it was not cool to do machine learning, then you did it. And now when it's really cool, you say like, oh, come on, we should do this stuff instead, right? Great. So effectively, what I'm going to try to do with this lecture is to stop you from starting to do machine learning straight away, okay? So, why do we do machine learning? Well, we do machine learning for, I think we can divide these things up into two parts. There's either tasks that are too hard to program, right? So you can think about things like speech recognition. This is really, really hard to come up with a set of rules to do exact speech recognition. To think about image understanding being the same thing. Both of these are examples where we have vast amounts of data, right? So we want to exploit the data for something that's simply too hard. And then you have other things which you might argue are like tasks beyond our capability. These two things we know exactly how to do, right? Hopefully you can recognize what I'm saying now, right? And you can hopefully identify that I'm Carl from visually seeing me. So you're capable of doing these two things, right? But it's just really hard to extract how I do this and write the program for it. And then you have another set of things which I would argue is like tasks beyond our capability. So take a thing like weather prediction, right? I can't do it. I don't think you can either, right? And we got things like web search or things that are just very, very hard to do. What we do then with machine learning, or what the thing is trying to do, is trying to bridge this knowledge gap we have by data in some form or way. And I like to show this by a plot, which some of you have seen, some of you might have not seen before. And this is here, is what I like to call the Pareto front of machine learning. So on this axis here, on the top, on the surface of this blue thing, you've got problems that are well posed in one way or the other. So it can either be well posed if I'm down here, so I have no data whatsoever, but I've got perfect knowledge of exactly how this works, right? I just plug something into an algorithm and you get the answer because you know how to do this. Well, the other end of the spectrum is that you've seen everything that's ever going to see before. So you can just chuck this into a database, right? You see something, well, now it's just a lookup table and you figure out exactly what you're supposed to do. And then you have the problems where machine learning really comes in, where I don't have enough data, and I don't have enough knowledge. And the question then is what the topic is really trying to do is being the glue that puts these things together. I know a little bit about weather, and I've collected a lot of weather data. Now, can I glue these things together so that I do something good, right? That's really what machine learning is. So now, in the learning procedure itself, and this is what we're going to talk a lot about, is biases come in. If we don't have biases, there's nothing we can do. So what you often think about in terms of machine learning, if someone presents algorithms to you, they say, this method assumes this, and this method assumes this, and then you try and choose which method you should use based on those things, right? Based on those examples. I think one of the arguments that we're trying to do is that most of the inductive biases that you want to exploit are actually done before you start doing machine learning, in the access and assess stage of the pipeline, right? So I'll give you an example. I went to a cardiology conference a while ago. So you've got these amazing doctors that are like saving lives, and then they're studying something as complicated as a human being, right? And then what they do, a PhD seems to be, I go out and I study this bizarre thing that we found. I'm going to take 150 patients and I'm going to get some stats on them. And then they draw a conclusion to come up with a treatment. Statistically, this makes no sense whatsoever. Right? Think of the parameter space of the human being and put 150 points in that. And now you're effectively fitting some curve to that. Does not work, right? It doesn't work. Why does it work? Because it proves that, like, they're saving lives. This stuff works, right? It's because all the inductive bias they put in of who should I actually go and get this data from, right? And then thinking about how should I treat and prepare this data? And then the last bit of this is when they do a little bit of stats on it, right? And it works, right? It really, really works, right? So the idea here is, you've probably heard it, but this notion of the 80-20, right? 80% of the work really happens before you do this last bit, right? Cool. So what I'm going to talk about then today, to stop you doing machine learning so quickly, is what is actually machine learning, and thinking about what can machine learning actually do, what are the limitations, what are the boundaries that we work with it. And I'm going to try and put machine learning a little bit into context. And we're going to end with introducing one type of method that's really, really useful, that's really effectively quite simple, but it will allow us to take all the other questions that we raised in a much, and put all the other questions into context of that method. And that's the one that we're going to work with. Great. So the way I'm going to introduce this is through the notion of statistical learning theory a little bit. So I'm going to try and tell you about how we can view learning as a theory itself, right? So what often people do when they teach machine learning is they would start off saying, I'm now going to come up with a set of paradigms, and then we're going to walk through these paradigms. You've probably heard these things. So I have something like supervised learning, unsupervised learning, reinforcement learning, federated learning, or meta learning, online learning, blah, 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 right? And then you can come up with these kind of things. I found this on the internet, where you can say, great, it splits up into all these things. And then what we'll do, we'll have one lecture on each one of these, and we'll teach you one method after the other. And then you have a good toolbox, and then you go around and smack it on stuff, right? But what I'm going to try and do is do everything the other way around instead. So I'm going to try and tell you fundamentally what machine learning is, right? So let's do some definitions just so that we have something to talk about. So I'm going to say that we have a domain set. This is a set of measurements that I take in the world of something. And I want to provide them, my task is to provide them with a label of sorts. It's classification, it's binary, or it's a discrete label set. If it's a continuous function, it might be a continuous label set. Okay? And then I have this label set itself. This is my set of outputs. So X and Y. Okay? And then I have access then, and this is the thing that when we come to this point, this is the thing that we've really curated, right? Lots of work goes into it. And now I have a training data set, which is some finite sequence of pairs in this product space, X, Y, okay? Now, what we have is that this finite set comes from some data distribution. So this is a probability distribution that governs these measurements, right? They have some form of structure, and those are encapsulated in this D. And then there is a data generation. This is the thing that maps X to Y. So this is the underlying generating process of the data that I see, right? Okay. And our task is to come up with some form of prediction rule H that maps X to Y. This is the thing that we want to recover. Okay. So if we simplify this and look at a binary classification task, this is what we have, right? So what I have is that I have a data distribution. It's these two Gaussians. I have a generating process, which is the thing that gives one side blue and one side red. And then I got some finite samples, these crosses from this, right? That's the task that we start off with, right? So then we need to come up with a method of some sort. So we need some measure of success, right? We need some measure that says, how well am I doing at any point of time? So let's think about this measure here. So what this measure would be is that I take, for any X, I put it through the hypothesis or the prediction rule, H, and I see if it matches the generating mapping, right? If it doesn't, it counts up this set. And then I take the probability of that set, right? That would be good. So if I'm perfect, this is 0. And if I'm doing really awful, then it's 1, right? Okay? So that sounds great, right? What's kind of useless about this thing? Why is this thing impossible to evaluate even? Exactly, if I knew F, you just make F equal to 8, right? Job done. Very good. It's another thing. You don't know D either. Exactly, I don't know D either. So this is useless, right? But this is the gold standard. This is what we would want to have, right? So exactly as he said, don't have D, don't have F, right? So what I really have is this, right? This is actually the task that I'm trying to do. This is what I'm given. So now, let's just reflect over this thing. So which data points are the only ones I'm not interested in giving a label? Exactly, those ones, right? So this is my training data. It's the only thing I don't care about, right? But what we do still, right, is this is also the only thing I have. So we usually think about the training data as a proxy, right? We think about if I do well on the training data, I hope I'm doing well on the test, because I think this is just not random nonsense. It has something to do with the underlying data, right? So what we would do then is that we will take something which we'll call an empirical risk, and we'll say, okay, I don't have the distribution, so I'm just going to count. I'll pick a hypothesis, and I'm just going to count the number of ones that are misclassified in the training data set, and I'll take the average of that, right? That seems like a good proxy. And this is called the empirical risk. Good. So then let's just take something, the best or really good hypothesis on the training data. So what I'm going to do is I'm going to give you this hypothesis that says, if I have the data point in the training data, I take the training data label. In every other case, I give it 0. So this, by definition, has zero empirical loss on any training data set. Now, let's say that these two were like a third red and a 2/3 blue, right? Now that means if it turns out the label 0 corresponded to red, my error, or my true risk, is a third, right? Or if it's the other way around, it's 2/3, right? So I'm guaranteed to do perfect on the training data, but I'm awful on the test data, right? So you also have to think about the hypothesis just doing well. It is a proxy, but we aim for this notion of generalization, right? Because we want to be good at other things. So then let's think about the first problem here, right? So here I have another data set. I had to make it a little bit trickier to do this graph to show some complication. So here I got this data set like this, and I'm going to train a classifier on it. And what I've done is that I've taken quite a good classifier. We don't need to really care about what it is, but I've taken a good classifier on this. And then I've taken the magenta one, comes from when I take 10% of this data at random and make it the training data set. And that classifier has 0 training error pretty much all the time, independent of how I pick it. And then I compute the error on the test, right? Now this here is a distribution of how well I'm doing, right? So for some training data sets, I'm doing really, I'm 50-50, right? I'm awful, I'm chance. And some others, I did really well. The other one here, the blue one, I think I took 20% instead, right? So now what I wanted to highlight with this is just the importance of the data set that you selected. Just this really simple example of classifying these are exactly the things that we've talked about before, right? Curating the training data set, preparing the data so that this distribution just looks a lot nicer, right? And this is still a lot of points for doing that result, right? It's not the doctors taking 150 points from a million-dimensional space. Cool. So that's the first thing. So those things we've kind of talked about, how you curate the data, how you make sure that the stuff you come in and you train on makes sense. That's really what Niels talked about. So then how do we input inductive bias? How do we continue doing this in the machine learning algorithm itself? Well, a machine learning algorithm, anything, has 3 components. So the first thing, how do I actually find my hypothesis? Well, that's kind of like a search problem, right? I have a set of possible things, and I have to walk around in this space and pick them, right? You can think about the gradient descent algorithm, for example. I've parameterized some form of classifier, and then I have to walk around in this space. I'm going to call that the algorithm. So use an algorithm that actually returns you a hypothesis. That's the first thing that we're in control of. The next thing is, you can't have parameterize every possible hypothesis. And you don't want to do that either. You want to have a finite set of hypotheses that you decide to choose from. I'm going to work only with lines. I'm only going to work with polynomials up to this degree, and so forth, right? I'm going to work with this neural network that has this architecture, right? So you're effectively searching over a subset of possible hypotheses, okay? So let me just go to this, okay? So that's these 3 components of the system. So you have the algorithm, you have the data set, and you have the hypothesis space itself. Those are the handles where we can structure the method that we use. Okay, keep that in mind a little bit, and we're going to come to the next thing. So when I showed you this thing about overfitting, that I said this silly thing does perfectly, now I'm going to show you that example and extend it to regression instead. Okay, so I've given you these 2 points, and as we clearly said, these 2 points are the only thing I'm not interested in. So I'm actually interested, let's say that we're interested in this point, just for the sake of it. Okay? So now your task now is to fit a function to this. How many different functions passes through these 2 points? Well,
I mean a linear function.
Excellent. Perfect. Cool. So you said it. You've already made an assumption. You reduced your hypothesis base massively and said it's a line. Cool. And in that case, it's true, right? But you've restricted the possible set of functions down to this. And that's exactly what we're always going to try to do, right? But let's make it even more general. So I'll give you some more points. How many points? How many functions? Infinite, right? Infinite, right? I can give you, if we started off talking about this point here, I can give you functions that pass through exactly these data points that give you any value between minus infinity and positive infinity, right? Which means if you don't make any restrictions, right, like you just did, which is exactly right, then I can't say anything about this point effectively, right? However, I think we all kind of nicely agree on that might be a sine wave, right? It is a noisy sine wave. Cool. So that bias that I put in that we all agree on, in this case, the machine learning method has no idea about it, so we need to input this, right? That notion of you thinking that's probably this, compared to any other infinitely many different functions I could have given you, that's a notion that we need to put into the system. So, effectively, every algorithm that does something useful does so by making some assumptions, by limiting one of these things. There exists no universal method learner at all. You can actually prove this, and this is what's called the no free lunch theorem of machine learning, right? There is no free lunch. Cool. So I then just wanted to hint at how we can input knowledge. We've got these 3 things: my learning algorithm, my hypothesis class, and my finite training data set. Neil's talked a lot about how we create this stuff, right? How we come up with a training data set, how we gather data, and so forth. So I wanted to talk about the other parts then. So the way we think about A, which is effectively our search algorithm, is that this is the thing where I have parameterized my hypothesis space. Say that it's all possible lines, right? Say for the sake of that. And now you have 1 point, but you really know that what you're looking at should have a positive slope, right? What you can now do is you can create an algorithm that when it walks around in this space, all the negative stuff is clearly on that side, right? So I'm going to just put an eye patch on that and make sure that it doesn't see them and bias it. It's a totally valid way of introducing a bias, right? This is really what's happening a lot in neural network training. This is where we input bias by choosing different methods to search for the problem so that we just find the solution that we want. The other thing, we talked about that a lot, is curating your data set. Or, except for the things that Neil talked about, you can also think about very simple things as, I have an image of my mum, and if I turn my mum upside down, she's still my mum. So what I do when I train my Carl's mum classifier is that I take all the images of her and I rotate them, right? And now I feed them to. Now I've introduced a symmetry to my classifier heuristic, right? Data augmentation. Definitely something that you can try in the lab. And then the last bit is thinking about then how can I construct hypothesis classes that respect these things, right? That I have a notion of that I'm looking at a physical system, for example, I know that it should be smooth to this degree. I know that it should always be positive. I know this and that. Now you can very clearly constrain your hypothesis class so you only have parameterizations that you're looking for. So now, there is a thing then, which you often talk about in statistical learning, of where if you find you have some training data, you pick an algorithm, you pick the hypothesis class, you run this, now you're going to get a solution, right? So H hat is the solution found by your learning algorithm. What I'm trying to show here with the red circle, don't think geometry here. This is completely abstract. Here is the hypothesis path I've defined. Okay? Now, this point here is the hypothesis that my method returns. This H hat opt is the optimal hypothesis on the training data. But there's a gap here where this was the one I found, but I designed this algorithm that picked this thing instead of that one. So this here has a smaller error on the training data. Okay? And then I have H opt, which is if I have all the data, this will be the best classifier in the set, in the hypothesis, in the class that I specified. And then I have H hat, which is the thing, which is the optimal thing. This is like H is equal to F. Could have really put F there, right? Okay. So what you can do now is you can decompose the error that you get from any method by looking at it like this. So this error here is the error that's induced by your algorithm. Okay. So this is you choosing something that's suboptimal in one way or the other. Then you have an error that's induced by your bias or your missample of your training data set, which is there. And then you've got the last error, which is the thing because you have the wrong hypothesis class, right? So now you can see by working on each of these different ones, you can reduce one error, right? This is effectively how the error decomposes. Okay, so the best possible machine learning algorithm that you can find, or model path that you can find, is if you have the smallest possible circle. So you have a method which is super inflexible. You can only do one thing, ideally, and that circle sits around that thing over there, right? Now I effectively need no training data because I've already given you the solution, because there's no variability that I'm searching for, and it sits over the correct thing. Right? So this notion, and why I wanted to show this notion that machine learning, we should always look for the most flexible thing that can do everything, is complete nonsense. Right? We should take the thing that is as inflexible as possible, but it should be inflexible in exactly the wrong way. Right? Cool. So, effectively, what I wanted then used to summarize the statistical learning bit was that there is no universal learner. There's no such thing that is good at everything. For everything that something is good at, there is something that it fails at, right? So every algorithm that learns something useful does so by some form of assumption. Another way of showing this is that machine learning is a zero-sum game. If you're good at something, you're definitely going to be bad at something else, right? If you're good at everything, you also know nothing. Karl Popper said this: the theory that explains everything explains nothing, right? Okay, good. So, if you're interested in learning more about this, because I'm not going to talk more about this now, I just wanted to set the scene for you thinking about these things. There's some really nice books. So this book is free as a PDF, and there's also this very nice lecture note course from Oliver Busquets, who I also really like. Cool. So now, having said all these things, if you take statistical learning theory, which is a nice theory, and then try to prove that this is specifically what we should be able to do, right? Machine learning would not be as popular because there is this mismatch, a massive mismatch between reality and what we do in practice. Machine learning is doing much, much better than we're theoretically supposed to do, right? Enormously much better. And what's this gap? Well, the gap here is really, I think, part of what we've been trying to get across in this course. So there's something called, so far, what I've been talking about when I talked about machine learning, I talked about what I like to call explicit knowledge, right? It's like a recipe. I can formulate these things, I can write it in a book, and I can tell you how it's done. But then there's another set of things which is called passive knowledge, right? Passive knowledge is like me riding a bike. I ride bikes all the time. I don't fall over particularly often, so I'm reasonably good at it. I cannot explain to you how you ride a bike, right? At all, right? Now, this part is very often forgotten in terms of machine learning. We always try to come up with things here, but we haven't really done that particularly well. And when it becomes really dangerous is when we do a misattribution of the narrative. So here is my, being Swedish, this is my football captain, Zlatan Ibrahimovic, on the 14th of November, 2012, we had the new national stadium, Friends Arena, this was the first game in Stockholm, and we beat England by 4-2. We're 2-1 down, and Zlatan scored this goal. There's a bicycle kick from half the pitch, right? The best thing about this was his interview afterwards, right? Exactly what you were saying about Haaland. His interview afterwards, he will talk about 5 minutes about what he thought about this. It's a complete nonsense, right? He's brilliant as a footballer. It was just instinct, right? Clearly. If you think, you can just think about how quickly the brain processes things. It's impossible to do this, right? He's acted and it worked, right? And that's great. And what we do a little bit in machine learning, I think, is that we forget that whole art of the topic and we just want to attribute stuff here. And part of that art is the thing of just doing things, right? We've seen a lot of these things so far in part of the code, and I just want to argue that the rest of it, the address part, has exactly the same things. Cool. So this gap is then filled by, as I said in the beginning, the access part. Enormous amount of inductive biases is introduced by you deciding what you should query. Assess the amount of human bias of the questions that you think will probably be asked. You kind of have quite a good idea of what we're going to ask you on tick 4 and the rest of the project. You have, right? Simply by this, right? That is already introducing a bias, right? So the last bit then, if you want to think about it, is just curve fitting. That's the only thing we do. That's what machine learning really is. But now when I've told you to stop this and I've dumbed down my field, I built a career on doing this because curve fitting can really be fun, right? Cool. So what we're going to do now for the last bit, when I try to demotivate you about machine learning for about half an hour, I'm now going to tell you the models that we're going to look at. So what we're going to look at is something called generalized linear models. Okay? So what we're doing this for is that we're going to find a much, much smaller class of hypotheses, and we're going to work within this. Now, these models are linear in their parameters. And why are we doing that? Because this thing, if you think about this finesse network or framework, as Neil talked about, nothing's ever static, right? Nothing's ever static. You need to go back and forth continuously. And in order to do that, we need to understand what these models are actually doing. If you throw some crazy neural network on this stuff, you won't be able to actually understand why did I get these results. And that's kind of the most important thing, because you get some results, then you want to be able to say, I should probably go out and query some data in this region, or I should actually tune this data in this way, and so forth, right? So that's why it's really important that we have an interpretable scenario here. And the other thing is that even if we didn't feed into our loop, so now let's think assessment, right? At one point in time, you need to give something out, and that's the end, right? Cool. Now, the most important thing is not to be the most exact. The most important thing is very often to say, I think this because of this, right? So having an interpretable model is really, really important. And I would argue the linearized models are generally something that we can actually reason about. So I'm going to again slightly change the formalism just to define these things, because this is what people call them now in the statistics literature. So we have an explanatory variable, your input, and I have a response variable, y. Now, top is to explain the response by the explanatory variables, right? Simple as that. So the simplest thing you've probably seen of this is linear regression. Right? This is one generalized linear model. So the only thing it does is that it looks like this, right? So I want to predict y. I do that by taking a linear combination of my input dimension, and then I can possibly add some noise to this. This term here is what we're going to use to generalize this. Right? So say that you now manage to pick one of these models. Okay, now you have to give me an answer for something. You have to make a decision. You have to pay something for this house, right? You built a house price predictor. Well, you can't give a stochastic price back to the bank. They're not going to be happy about this. So what do we do when we do a prediction there? Well, we would take the expected value of this predictor. Okay? So if I take the expected value of this, I have the linear predictor, and then I got this noise term on the end. Okay? The noise here was Gaussian. What I can do is I can split that expectation up like this. This is the sum inside an integral, right? So I just make two integrals out of it. Now, this thing here is just completely deterministic. There's nothing in here, and no beta in this case, we assume. I know the inputs. This thing here is the expectation of a Gaussian, which is just mean, right? So the only thing I have is this plus this, right? So that's probably the way you thought about and seen how you do a prediction using a completely linear regression model, right? So now let's generalize this to get to the generalized linear model. So we have this expression, same thing as before. What I'm now going to do is that I'm just going to move the epsilon over to the other side, right? I just do this, okay? So now I say, instead, semantically, this makes a difference. So now I say, I got this linear predictor that predicts the stochastic variable. So I'm going to write that clearer and say it like this. So I have a linear predictor with predict some variable that follows some distribution. Okay, y hat. So in the previous case, which we had, epsilon was Gaussian, right? So it's just says that this response variable that I have follows a Gaussian distribution with this mean and the variance being the one that came from before, right? From the error, right? Nothing strange about this. I've just moved terms around. But semantically, this is going to be important. So what we're going to say, and this is where the generalization comes in. So a generalized linear model has these terms. So what it says is that I have a linear predictor, and the linear predictor predicts the first moment of the expectation over the response variable through this function called g. Right? So g here is called the link function. I'm going to show this one in another order, and it's going to be a little bit more interpretable, but this is how it's always written if you find the Wikipedia page or a course book like this. It's always written like this. We're going to say that y comes from a family. Remember, we said the response now follows some distribution. It's going to come from a family of distribution called the exponential dispersion family. Pretty much any distribution that you've ever heard of will come from this distribution, right? It's something that has a mean, and then it has a dispersion around it, like a Gaussian, right? Mean variance, but there's lots of distributions like this, okay? And then the relationship with the input variables is always linear. That's it. So these are the parameters I have of the model. Okay. I'm going to flip this one around and it looks a lot simpler. So what I have here is that I say that I have a linear predictor, then I take the inverse of this linked function, and that gives me the first moment of the explanatory variable. So if I had a linear predictor, and then I say that y was distributed as a Gaussian, what would the linked function be in that case? We showed it before. Remember when we took the expectation, I just moved things out? What did it end up being? Yeah, you're saying the right thing. Someone's saying exactly the right thing. Exactly, it's identity. So for a Gaussian, this is just the identity. Yeah, right? That's why I shifted things around to get to this more generalized thing. Okay, so for the linear regression case, the normal one you know with Gaussian noise, it's just an identity function. Okay. So it also, if you think about this inverse and you know about neural networks, it looks an awful lot like what a neural network is. You just chuck several of these ones in a recursion. Okay, I'm not going to go further with that. Cool. So what we're going to talk about, because we're wrapping up, is now this formulation of something summarizes a lot of incredibly useful models. So you've got linear regression. That means that the response variable is normal. The link is identity. And that means the explanatory variable is now a continuous explanatory variable. Now, what I can also do is I can say I have a logistic regression. Now, the response variable is binomial. So it's a classifier. It's a class. Now, the link function is a logit, and so forth. We're going to look at a few more of these in the next lecture, and we're going to do some in the lab. But this system here just generalizes a lot of models. And the only thing you're doing is that the predictor is always linear. So you take your response variable, whatever that is, house location, this. You learn a linear weight on each one of them. That linear weight you can always interpret and say, oh, this one is much more important than this, and this one's less important. That's where the interpretability comes. But the output can now have lots of different types of distributions. It can be a classifier, it can count counts, for example, if you've got this Poisson distribution, all this stuff. Right? We're going to talk a lot more about this later on. But what we're going to use a very nice package to do these things, where effectively these ones are the inputs to them. Right? Cool. So I'm just going to summarize and wrap up. So what did we do today? Well, I gave you a very brief introduction to statistical learning theory, because I'm tired of giving these talks, which we gave 10 years ago, where we said, this is magic, come and listen to us, give us lots of money, this is the future. We realized it isn't the future because Facebook and other stuff happened, right? Cool. So the take-home message then was that machine learning, models, algorithms is only a very, very small part of the story here, right? A lot of the biases to deal with the no free lunch comes in beforehand. We are doing a lot better than we should. Like the theory of machine learning is way behind what we're actually doing in practice, right? Where does this come from? It comes from the art form of doing this stuff, right? Cool. And we're not really sure why this works. Some people are working on this. Some people in this lab are working on these things, and it's quite exciting, but there's still a massive, massive gap. So in some way to summarize that, it's not the explicit knowledge that pushes data science forward, it's a tacit knowledge that sits among all these data scientists who actually do stuff. And in order to do that, we need to train ourselves, right, by actually doing this. And that's why we pick this reasonably simple model. And then afterwards, you can take all these courses, the next 2 terms, and you can go and run with lots of cooler models. Great. So what we're going to do then is that tomorrow, we've got a lab where we're going to work with these generalized linear models. Then I'm going to do a lecture on that. And then we're going to have, we don't have a lab on Thursday, I believe. Am I right? Yeah. So the tick on that will happen on the 15th. Right. Cool. Do we have any questions on things? No questions whatsoever. Okay, good. So then we'll see you guys in the lab tomorrow, and we'll start working through this. And then the lecture after that, what you're probably going to do is learn these the other way around, which I think is really good. So we're going to go and practice on these things, play around with them, and then we're going to go back on the lecture and actually looking how did inference work in these? What were the things? Because we got this really nice software package, and because it's linear models, we can kind of interpret them and kind of trust them. Right? Cool. Very good. Thank you very much.
You mean to have to remind me?